Hi everyone, I'm Romil, and today I'm going to talk about Cilantro, a general framework for performance-aware resource allocation. This is joint work with my colleagues at UC Berkeley and University of Wisconsin at Madison. So let's look at how resource allocation works in multi-tenant clusters. Say you have a cluster of 100 CPUs you want to share amongst two users, Alice and Bob. Alice is serving a database and has a service level objective, or SLO, of 100 queries per second. And Bob is serving a machine learning model and wants a SLO of 50 queries per second. A fundamental question here is, how do you divide resources between Alice and Bob? The simplest way to do this is to equally allocate resources to Alice and Bob. So we give 50 CPUs to Alice and 50 CPUs to Bob. But after Alice and Bob run their tasks, they realized that Alice needed only 20 CPUs to serve her queries on time, whereas Bob needed 80 CPUs. So we effectively gave Alice 30 extra CPUs, and Bob got 30 fewer CPUs than he needed to serve his SLO. So we can see that equal shares are fair, but they are inefficient. To work around this, most modern schedulers like Kubernetes, Slurm, and so on, they ask users how many resources do you need to run your job. But now the problem is users often don't know how many resources they need to achieve their SLOs. So instead of providing accurate resource demands, they provide estimates. So Alice estimates that, oh, I'm going to probably need 60 CPUs, whereas Bob estimates he'll need 40 CPUs to serve his job. And if we end up using these demands, we again give Alice 40 extra CPUs than she needed, and Bob gets 40 fewer CPUs than he needed. So inaccurate resource demands result in inefficient resource allocations. So taking a step back from scheduling based on resource demands, we can see that users do not have well-defined resource requirements. Instead, all they have are performance objectives in the form of their SLOs. So the question then becomes, can we allocate resources directly based on users' performance goals? We call this performance-aware scheduling. More formally, users know their SLOs, but not the resources required to achieve their SLOs. A resource performance curve can map these SLOs to resource demands. Here is an example. This is a resource performance curve for a query set of TP-CDS run on a very simple SQLite database. On the y-axis is the throughput, and on the x-axis, you can see the number of CPUs required to achieve that throughput. For a given SLO, we can estimate the number of CPUs required by using this curve. For example, if my SLO is 100 queries per second, you can see that using this curve, I can derive I need 30 CPUs to achieve that SLO. Unfortunately, the challenge here is we do not know this curve ahead of time. And even if you know this curve, you cannot, and if you do not know this curve, you cannot estimate the number of resources you need to achieve the SLO. So say we assume that we know this resource performance curve. Even then, how to allocate resources between users remains a question, especially when the cluster does not have enough resources to satisfy all SLOs. Say, for example, we now have 20 CPUs instead of 100 in our cluster. And we know that Alice needs 20 CPUs for her SLO, and Bob needs 80 CPUs. Now the question again is, how do we split resources between Alice and Bob? In such situation, a cluster manager steps in and declares an objective for the cluster. These objectives can either be performance-based, such as maximizing the average QPS across all users, or resource demand-based, such as classical maximum fairness or priorities. The resource allocator must then optimize for these objectives. Now, since different organizations may have different scheduling objectives, this diversity necessitates a general resource allocator that can optimize for any objective provided by a cluster administrator. So to enable performance-aware scheduling in multi-tenant clusters, we built the Cilantro scheduling framework. Cilantro solves the two key challenges to performance-aware scheduling that I just mentioned. The first challenge was that resource performance curves are unknown ahead of time. To address this challenge, Cilantro collects feedback from jobs and uses online learning to continuously update resource performance models for running jobs. The second challenge was we need to support a diverse set of objectives. Cilantro enables this generality by decoupling the resource allocation policy from the learning mechanisms that are used to learn these models. And in doing so, the resource performance models that are generated, they act as an intermediate layer that any policy can use to achieve the objective stated by the cluster administrator. So let's look at how Cilantro works. The policy in the Cilantro scheduler contains the objective defined by the user. This policy then produces a resource allocation and passes it to the cluster manager, which allocates these resources to different jobs. Each job then generates feedback, which contains the observed metrics, such as the latency, the SLO, and the current load on the job. Think of the load as a very simple metric which reflects the amount of work which is pending at a job. This feedback is then ingested by online learners running inside the Cilantro scheduler, which record the performance for a given resource allocation and update their model to produce a new resource performance mapping. These models improve over time as learners collect more and more data. And these performance models are then again used by the policy, and this closes the scheduling loop where the policy now produces a new resource allocation, and then the learners learn again. So using online learning for resource allocation presents two key challenges. First, the search space for the online learners is both large and expensive. And second, the model estimates produced by the online learners have uncertainty, which is usually expressed in the form of confidence intervals. This uncertainty is particularly large at the start of the job, where we don't know how the job is going to perform. And eventually, as you get more data, it improves. So we address these challenges in Cilantro in two simple ways. First, we reduce the search space by defining a constrained utility model. And second, we make policies in Cilantro uncertainty aware, which allows it to conservatively explore the search space when uncertainty is high, and aggressively exploit when a good resource allocation is found. Let's look at both of these solutions in detail. So as we discussed earlier, each job has a resource performance curve that is unknown to Cilantro. This is shown on the right here. Each job also has a SLO, which is a service level objective, which is the performance goal set by the user. This is the green dotted line that you see. In Cilantro, the user must define a utility as a function of performance. And this function must have two critical properties. First is it should be monotonically non-decreasing. And the second is it should be clipped at the SLO. That is, any additional resources beyond what are required to achieve the SLO should not increase the utility of the job. The blue curve on the right shows an example of a utility function derived from the performance. These properties are important because the monotonicity property makes the exploration more tractable for the online learners, and clipping the SLO is reflective of how real-world utility works for more users. That is, they typically don't care about getting more resources than what are required to achieve their SLO. With this utility model, we can now define some commonly used scheduling objectives. First is general performance-based objectives, which aim to maximize some function of utility across all jobs. For instance, social welfare tries to maximize the mean utility across all jobs, whereas egalitarian welfare tries to maximize the minimum utility across all jobs, trying to ensure there's no starvation. Expressing these objectives is not possible in classical demand-based frameworks, but Cilantro can do this very easily. In addition, Cilantro can also do application-based performance objectives, such as minimizing the end-to-end latency of a collection of microservices. So given one utility signal, this objective aims to maximize the utility by allocating resources to a collection of microservices which are indirectly driving that signal. And finally, Cilantro also supports demand-based fairness objectives, such as NJC fairness. NJC fairness, or no justified complaints fairness, is very similar to maximum fairness, where it tries to minimize any fairness violations from the fair share that each job is entitled to. However, all of these policies, as they're stated right now, are not aware of uncertainty that may be in the utility function U or the load function L. So to produce good resource allocations, Cilantro must incorporate a model's uncertainty that is the confidence bounds in its policies. So Cilantro uses the optimism in the face of uncertainty, or OFU principle, to guide its policies. OFU is a well-understood and powerful algorithmic principle used in many regret minimization problems. What it states is, when an agent is presented with a set of actions and unknown payoff for each action, OFU suggests prioritizing actions which have the highest potential utility. In other words, we use an optimistic upper bound to guide our choice of action we take. So allow me to explain how this works with an example. Say we have 3 actions to pick from, and each action has its own payoff. This payoff is shown, this real payoff is shown as a red dot, and this payoff is unknown to us ahead of time. So we bootstrap our learning models with some initial expected payoffs and the confidence bounds for these payoffs. So in this specific situation, applying OFU would pick action 1 because it has the highest upper confidence bound. However, after picking this action, we realized that the actual payoff was low. So our models correct themselves, and they reduce the upper confidence bound estimates. And now, if we make another selection at round 2, we'll pick action 2 because it now has the highest upper confidence bound. Now, because action 2 has a high expected real utility, we see that in the next round, we get a high payoff, and thus our models update, and we get better and more confident bounds for the payoff that we'll get in future rounds. So we continue picking action 2. So in summary, the OFU principle allows policies to use confidence bounds to balance the explore-exploit trade-off when trying to minimize the chosen objective. So let's look at how Cilantro adapts our scheduling objectives to become uncertainty-aware using OFU. This adaptation is fairly straightforward because of the decoupling that Cilantro provides between the learners and the policies. So for performance-based and application-specific objectives, we simply replace the utility and load estimates by the upper confidence bounds from the models. This transparently applies the OFU principle to the objectives specified by the user. For demand-based objectives such as NJC fairness, that is slightly more involved, and the math is all in the paper. I would encourage you to check that out. So we have applied and evaluated Cilantro on 2 use cases. First is multi-tenant cluster sharing, in which a fixed pool of resources must be shared amongst independent jobs to maximize an objective provided by the cluster administrator. And the second is resource allocation for microservices, in which a fixed pool of resources must be allocated to different microservices belonging to the same global application. The objective in this setting is to minimize an end-to-end metric, such as the query latency, by optimally allocating resources to each individual microservice. Today, I'll present only the microservices evaluation, but please refer to the paper if you're interested in the cluster sharing experiments. So let's see how Cilantro can allocate resources to competing microservices. We take the hotel reservation benchmark from Death Star Bench, which serves as a reservation application powered by 19 microservices. And the way it works is a user dispatches a query to a front end. And then this is powered by a mesh or like a graph of microservices that do some computation and produce a response. With Cilantro, we observe only the end-to-end query latency to automatically identify any bottleneck microservices and allocate resources to individual microservices to minimize the response latency that we see. We note that Cilantro does not have any visibility into the structure of the microservices or their individual performance. It just uses the end-to-end latency to optimize the resource allocation. So I'll be comparing the P99 latency over time for 3 different baselines: resource fair, which equally allocates all resources, an epsilon greedy approach to explore exploit, and an evolutionary algorithm to find the best resource allocation. We find that Cilantro is initially conservative in its exploration, but as its estimates become more and more accurate, it is able to quickly converge onto a resource allocation that reduces the P99 latency to 43% of the next best baseline. So to summarize, Cilantro is a general performance-aware cluster scheduling framework. It presents a marked departure from resource demand-based scheduling, where instead of submitting resource requirements, users submit their SLOs and provide feedback. And online learning uses this feedback to learn resource performance curves and generates uncertainty-aware policies which optimize for the user's objective. And with this, I'll be looking forward to any questions.